Okay, so let us look at the issue of specification and related matters in terms of data. Um, so usually what we want to look at under this chapter, we want to look at the test for functional form misspecification. So we want to see whether the function is misspecified, and if it's misspecified, what type or in what form. Is it in the context of omitting a relevant variable? Is it in the context of including an irrelevant variable, or is it any other type of misspecification? Usually we would actually look at how the explanatory variables should appear in the model, and we would like to know whether they should appear, as with the predictability of 1 to the power of 1 to the power of 2 or to the highest power, whatever the case might be. Should we include them or should we exclude them? And so we can use some formal tests such as the regression specification error test, the so-called reset, and usually the reset or the idea of this test is basically to include the squares and possibly the higher order fitted values in the regression. And you can actually see the functional specification is like this. So usually we would like to test whether to exclude this or not, because under normal circumstances we would want to include them, but what if they are not relevant for that model? Then we would need to exclude them, and so that we can avoid the misspecification of the functional form, and that's why we do that particular test. And so, but one of the challenges that when you include you know high order terms, usually it becomes very complicated in terms of interpretation. And so one way, and that's why it's not always so easy to do. um, One of the shortcomings for this reset test is that it can tell you whether or not there is a presence of misspecification, but it can't really tell you what the source is. And so therefore that is one of the shortfalls of this type of test. All right, now we can actually use a number of ways to test for this. So one way we can actually use the testing of nested models against the non-nested models. Let us assume that we have these two models where we have the one which is basically specified in its level form, and then we have the one that is also specified whereby the explanatory variables are in log form. But you can actually see that the dependent variable is defined the same. Now, so if we actually just specify a general case where we have a combination of all of them, contained in one model, then this becomes the non-nested model, and this becomes the nested models because these are subcases of this one. So what happened is that if you have such, you can actually then test whether or not to include or exclude the terms, and you definitely have a clear winner. But this type of approach cannot be used if the dependent variables are defined differently. So say for example, if one of these dependent variable was probably in log form or what any other form different from the other one, we could not use this approach of testing or pitching the nested models vis-a-vis the non-nested models. So it can only work when you have dependent variables being defined in the same way. But now what happens if we have an unobserved explanatory variables? Usually what we do in that case, obviously um, that would actually then sort of constitute an omission of a variable or a relevant variable. So we have an example here where we are looking at the wage equation where we would want to look at whether the return to estimate the return to education and experience on remuneration. So suppose maybe now we would like to determine whether ability does also have an impact on the remuneration. Obviously we have to use a proxy. We have to replace that variable using a proxy, and that proxy, for example, in this case they can use IQ. So if they use the IQ, then so that will be a proxy for ability. So the general approach for using proxy variables is that it actually used when there is an omitted variable. Okay, so if there's an omitted variable, so you use a proxy for it. Now, what we should understand is that there are assumptions that goes as to when to use this proxy variable method or in order for this method to work. So this proxy is only a proxy for the omitted variable. In other words, it does not belong to the population regression. And now because of that, it actually then implies that it satisfies the classical linear assumption that the that proxy would not in any case be related with the error term, so meaning there's no correlation between the two, and so that's why it does qualify to be used. And secondly, it must be a good proxy, to represent the omitted variable. And it must only be used if all other variables that could be used will not help in predicting the omitted variable. And so therefore that would also imply that the correlation between the error term or the error variance of the proxy with the other existing explanatory variable should also be equal to 0, such that if you put x1, x2, and x3 in the model, you wouldn't have any problem. And also it also implies that all these variables are not correlated with the error term. Okay, and that's why we show here that the correlation between that variance or the error term of the third variable with the other explanatory variables is not existent at all. Okay, so it's only under certain assumptions that the proxy variable method can work. Okay, so for example, if we take this regression, right? So if we add that x3 as an additional proxy. So we can basically see that, for example, in this regression model, the error term is uncorrelated with all the explanatory variables, and that is one of the requirements. Secondly, so therefore that actually implies that all the coefficients in this model can be estimated using the OLS. Okay, so remember that x1, x2, x3 are the variables, and then the error term here is mu plus beta 3 v3. So we can then also say the coefficients of the explanatory variables x1 and x2 also be correctly identified, and the coefficients for the proxy variable might also be of interest. Of course, it's a interactive term because you have beta 3 rho 3, so it's a multiple of the coefficient of the omitted variable. Okay, so for example, if we take the wage equation where we are basically saying that variable IQ does fulfill the condition because it's not a direct wage determinant. Okay, in other words, what matters is how the person is able to prove at work. Okay, and then secondly, that is that the variation in the ability should be explained by the variation in the IQ score, and only leaving small of the variation or the rest or small of the rest of the variation to the rest of the variables such as education and experience. And then of course another way that we can use the proxy is probably by use the lag dependent variable. In other words, we take the dependent variable as one of the explanatory variables, but in this case it must be lagged. Okay, so if we, for example, want to represent if we want to represent an omitted variable or unobserved factor, we can actually use a lag dependent variable. So we have, for example, if we take this equation, the equation on crime, and we want to see how unemployment and expenditure affects crime. So if we have another unobserved variable, so we can use crime lagged by one period as one of the regressors to represent the unobserved factor or omitted unobserved variable. Okay, so and it also makes things easier to deal with, because obviously we know that the past crimes do somehow control for many omitted determinants. Okay, and then we also know that it makes it easier to do the interpretation, especially if you are dealing with different cross-sectional units such as many cities, because crimes in different cities cannot be compared. For example, if you have a crime, the crime happening, for example, in Cape Town cannot be compared to the crimes taking place in Joburg or in Durban or any other town. Okay. Okay, so then lastly, let us look at the models with random slopes, or what we refer to as random coefficient model. So if we consider this model, so what you have here is yi as a function of obviously this alpha plus ci. This is your average intercept and the random component, plus b, this is your average slope and then your random component, xi. So this model has a random intercept and the random slope. And so if we rewrite it like this, then it will actually look like this, such that yi is a function of is alpha plus beta xi plus ci plus dixi. So which is basically the error term. So what we have here, we are assuming that the expected value of ci given xi is equal to the expected value of di given xi, and we are basically saying that this must be equal to 0. In other words, the individual random components are independent of the explanatory variables. Okay, that's what we are saying. Individual random components, and the random components here is basically your di and ci. So they are independent from the explanatory variable. And then, so if that is the case, then we can basically then say the expected value of ci plus di xi given xi is equal to 0. And so that is the mean, and this is the variance. And we can then actually say we can use the weighted least square or ordinary least square with robust standard errors, and this will still yield consistent estimates of the average intercept and the average slope in the population. Okay, so that's basically just what we wanted to highlight in this context.